Hello and thanks for listening. My name is Mike Harrison. I'm with Gasbarre Thermal Processing Systems, and today I was going to talk about how ancillary systems included on nitriding equipment can impact the bottom line. Just a little bit about myself. I'm the engineering manager at Gasbarre Thermal Processing Systems in their Industrial Furnace Systems division. I have a Bachelor of Science in Engineering in Material Science and Engineering from the University of Michigan. I have an MBA from Walsh College. I have about 15 years of commercial and captive heat treat operations experience working in quality, operations management, and general management. And I'm a graduate of the 2019 MTIS program. In this presentation, I'll spend a little time talking about the nitriding cycle with a brief overview of the process. We'll talk through some of the various ancillary systems that might be offered as part of a nitriding furnace package, including vacuum pumps, external cooling systems, and atmosphere cooling systems. We'll talk through some test results on how these systems perform and their impact on the nitriding cycle. And then we'll talk through some of the potential savings that adding these systems onto a nitriding system can offer. And then finally some last acknowledgments from our testing. It's not really a secret in our business that time is money. In most cases, the goal is to get the parts in and out of the furnace as quickly as possible. Unfortunately, nitriding typically is a slow process, and so it works against us in terms of time. The diffusion of nitrogen is slow in order to develop the case depth and white layer required as part of the process. And the user doesn't really have too many options to speed that up. You may be able to run a little bit hotter, adjust some gas flows or atmosphere parameters, but you're really usually limited in the final requirements of the part in terms of surface hardness and case depth. So what about the rest of the cycle? Do we have options there to try and speed up the time before nitriding and the time after nitriding? Here we have an example of a typical nitriding cycle with the basic process steps shown. A first step might be a purge of the furnace chamber to help remove any air or oxygen from when the chamber was loaded. Usually this would be done with an inert gas such as nitrogen. Then you'll heat the furnace up. Sometimes there might be a pre-oxidation step included. So there'd be a brief hold at an elevated temperature. Air is added to the furnace chamber for oxidizing. But then after that, another purge step would have to be completed, as you need to remove any air or oxygen from the furnace chamber prior to ammonia being added. Those two gases at elevated temperatures can create a dangerous and explosive situation. So that'll need to be purged out first. Then you can proceed on to heating up to the desired nitriding or nitrocarburizing temperature. And during this step, it may be beneficial to start flowing some ammonia to the furnace to allow some dissociation to occur and to help get the atmosphere settled prior to reaching your set temperature. Then you proceed on with your nitriding and nitrocarburizing step as required. And then finally, there'll be a purging and cooling step to stop the process and to get the parts to a point that they're cool enough to then remove from the furnace chamber. As I mentioned, there's not typically a whole lot that can be done to achieve meaningful time savings from a nitriding step. You're limited by the diffusion of nitrogen into steel and the rate at which that occurs. There could be a little bit that could be done to speed up the heating rate depending on the size of the heating system on the furnace. But again, you do have to be aware, if you heat too fast, you'll heat the outside of the load up to your desired temperature, but the inside of the load will still lag behind, and you may need to wait while you're at temperature for the rest of the load to be uniform prior to nitriding. So again, there's kind of limited options there. But what about these times when we're purging and cooling? Those are times at this point that are really non-value added, and what can be done to help eliminate or reduce those times during your furnace cycle. So what if we can take that time and temperature profile and shift it to the left by reducing those purge times and cooling times to create an overall shorter cycle? Our nitriding time itself is the same, but now those times before and after those steps have been reduced, and to help us improve that overall cycle time. So one of the first options that we have to look at to add to a nitriding furnace is a vacuum pump. Now, these furnaces are not designed to be a true vacuum furnace, but we can use the vacuum pump to help on the purging steps, to help speed that up and to help ensure that we've got the furnace fully purged of any air or oxygen that could be in the system before adding any ammonia. So the model shown here, and you can see the system highlighted in green. You have a vacuum pump, and then the associated piping and valves to draw the atmosphere out of the furnace retort, through the vacuum pump, and out the exhaust at the top of the furnace. And again, along with associated valves to keep the pump isolated from the ammonia atmosphere while the process is running. The next system, and so this system consists of an air blower, piping, and valves that run underneath the furnace and into the furnace chamber to provide that external cooling. Something that we have available to add to a nitriding furnace is an external cooling system. And so the way this furnace operates, there's a sealed retort inside the outer furnace chamber where the load sits, and that's where the process gases are added. And that stays sealed up during the process, and so the heating system is around the outside of that retort, inside the outer furnace case that we're looking at here. And so with the external cooling system, what we can do is, again highlighted in green here, we can take an air blower and we can run ambient plant air into that heating chamber on the outside of the retort. So again, the parts inside the furnace being processed are still sealed and protected. But then we can run air around the outside of that retort to help extract the heat from the retort and exhaust it out of the furnace to help speed up any cooling rates. The last system we're going to look at for this presentation is an atmosphere cooling system. The purpose of this system is to circulate the atmosphere that's inside the furnace, inside the retort, cool it down, and then send it back into the retort to help extract heat from the load that's being treated. And so this system includes a heat exchanger, a recirculating blower, and then the associated piping and valves to isolate that system while the nitriding process is running. The heat exchangers typically used for these are not rated to handle ammonia, so the furnace will need to be purged prior to operating the heat exchanger loop. Although there are heat exchanger systems that can be used to help cool, that can handle ammonia running through them as well. They do become more costly, but those are available if even faster cooling rates are desired, so those systems can come on immediately as opposed to waiting the appropriate purge time first. But for the purposes of the testing that was done for this presentation, we used a heat exchanger that was can really only see a nitrogen atmosphere, so there was some purge time required prior to starting this heat exchanger loop. Now I'd like to get into looking at the test results from each of the ancillary systems presented. So first I'd like to define some of the test parameters. The furnace load size that was used for these tests was 48 inches wide by 72 long by 40 inches tall. The furnace had a rated load capacity of 7,000 pounds. There was a 5,500 pound load placed in the furnace during these tests. And the furnace was run up to 1050 Fahrenheit prior to the start of the cooling cycles. First we're going to look at test results using a vacuum pump. So if we only purged the furnace using nitrogen, the furnace has an available flow of 1,000 cubic feet an hour. The total volume to be purged, which to meet safety requirements per NFPA would be 5 volume changes of the retort before being considered acceptable to add ammonia to the system. So we had to purge a total volume of 1,375 cubic feet. And so that's a time of 83 minutes to complete a single purge step. If we look at using a vacuum pump to achieve a similar purge step, the vacuum pump used is a 15-minute time to reach a vacuum level of 5 torr. Then there's a nitrogen backfill that has to occur in order to repressurize the retort prior to proceeding on the cycle, and that's about a 15-minute time as well. And the total gas used during this time was 250 cubic feet. So in all, there's a 53-minute savings by replacing just a purge-only step to instead using a vacuum pump with a nitrogen backfill afterward. Next we can look at the trials run on the cooling systems. And so if you look at the graph here, you can see the cooling rate over time for the various cooling systems. So the red line at the top would be no additional cooling on the furnace, so that was simply turning the heating system off, leaving the recirculating fan running, and allowing the furnace to just cool naturally on its own. And as you can tell, it's a very, very slow cooling rate. And if you were to extrapolate that line out to attempt to reach the 200 degree cutoff we were shooting for, it looks to be about 6.5 days of cooling time, which is by no means practical for any operation. So then if we look at using the external cooling system, this would be the green line on the graph. Again, this system is just the air cooling around the outside of the retort, significantly improved over no cooling whatsoever. And so that cooling rate to get down to about 200 degrees ran about 8.5 hours. Then the blue line, adding the atmospheric cooling system in addition to the external cooling system. So this would be recycling the nitrogen that's in the retort out through the heat exchanger and back into the retort again. And you can see, as I mentioned previously, there's a purge time that has to occur prior to allowing that heat exchanger to start. And then you can see where the blue line starts to split from the green line as the cooling rate increases once we're using the atmosphere cooling system. And so that gets us down now to about a 5.5 hour cooling time using both those systems. And so as you can see, there's about a 3-hour time savings by adding the atmosphere cooling in addition to the external cooling system. So now as we start to get into some of the savings and justifications that can be used for these systems to be added to a furnace. First we have just set up some assumptions on the cycles and what you can use to help justify these systems. Again, these will vary based on your particular process requirements or needs. So if we look at Both a nitriding and a nitrocarburizing cycle typically could be performed in the same furnace. We're assuming, for the sake of our conversation, the purge step would be 1 per cycle. The total cycle time on a nitriding cycle, again, these times will vary based on a particular process or a need, but a good average time might be 72 hours for a nitriding cycle, and maybe 14 hours for a nitrocarburizing cycle in this style of furnace. So over a course of a year, again, depending on how many hours a plant or an operation runs, you may be able to get 100 cycles in at 72 hours each, or 600 cycles in of a 14-hour nitrocarburizing cycle. If we assume the cycles end at 200 Fahrenheit, the external cooling system, we assumed it would be included. As you could tell from the previous graphs, again, not having any type of cooling just isn't practical really in any way. So we're going to assume that's already included as part of the system. And then the operating cost to run a good average might be around $60 an hour. This would be including utilities, process gases, labor, and any overhead required. And of course this will vary as well. It's based on your local utility costs and labor costs for a particular operation. So if we look at the vacuum pump with these cycle parameters, there was just under an hour's worth of savings at $60 an hour. It gave us a $54 savings per cycle. And so if we look at the number of cycles over the course of a given year, you can see on a nitriding cycle about $5,500 worth of savings. On a nitrocarburizing cycle, again, you're running many cycles. There's many opportunities to run that pump and shorten the purge timing, looking at potentially $32,000 in savings. And then with the atmosphere cooling system, it was just under 3 hours worth of time saved. Again, at $60 an hour comes out to about $174 per cycle. And again, over the course of a year, you can see just over $17,000 for the savings on a nitriding cycle, and a significant savings, over $100,000 on running nitrocarburizing cycles. Again, just by eliminating the amount of time required to complete those cycles. So if we look at the combined systems, in total cost savings from an operating rate standpoint, exclusive nitride cycles are looking at potentially $28,000 a year in savings. From a nitrocarburizing standpoint, very significant, almost $137,000 worth of annual savings by adding these systems onto a furnace. If we look at it in terms of hours saved, again, looking at running the same number of cycles, but now at a faster or lower overall cycle time, you're looking at 380 hours from a nitriding standpoint, potentially 2,300 hours from a nitrocarburizing standpoint. So if you were to translate that into additional loads processed per year, and then think about the additional revenue that can then be generated without needing to necessarily add additional furnace capacity, you're looking at an additional 6 cycles a year on the nitriding side. It doesn't sound like much, but it does add up over the course of time. And on a nitrocarburizing cycle, you're looking at significant, potentially 250 or so additional loads processed per year. So there's a potentially sizable amount of additional revenue that could be added to your operation without necessarily adding additional furnace capacity. So just to recap, time is money. It's really as simple as that. So when these ancillary options such as vacuum pumps, cooling blowers, heat exchangers are presented as additional add-ons or options to a nitriding furnace, they should really be considered and really need to look at what the benefits of those systems are and how they can help improve your operation from a financial performance standpoint. They can generate additional revenue and additional savings. As we previously showed, the time savings that are generated frees up furnace time that could be used for processing additional loads, and so therefore additional revenue is created without having to necessarily expand the operation. And these items they're typically about a 1 to 3 year payback, potentially faster yet, depending on the product mix and the type of cycles that are run. But they really are quite affordable and can really give a lot of benefit to the operation. I do have a few acknowledgments I'd like to make. I'd like to thank Neil Merrill and his team at Contour and Chuck Thomas with SSI for their assistance in helping organize and process these trials for us. And with that, I'd like to thank you for listening to this virtual presentation. If you have any questions or need any further information, my contact info is shown on the screen. Thanks again.